Hi, everyone. Our paper is The Pitfalls of Simplicity Bias in Neural Networks by Shaw et al. They claim that neural nets lead to extreme simplicity bias. They face the following conundrum in the literature. Simpler models generalize well. They have good results on test data. That is, simplicity is a good thing. But neural nets are not robust. They have poor results on noisy data or outliers. So noisy data is bad for neural nets. So they wonder, how can these two things be true? The reason, they say, is that neural nets lead to extreme simplicity bias. That is, reliance exclusively on simple features, even when more complex features are better predictors. For example, how are neural nets oversimplifying? Consider the following data set. We want to maximize the margin between the two classes. So we might choose a classifier like this. But neural nets prefer simple classifiers, so they are going to put more weight on the simplest feature, even though it's not the best predictor. They have two data sets used. One is called LMS, which has a simple linear coordinate, which is not the best predictor, and a complex coordinate, which is the better predictor. Then they have LSN, which is simply adding Gaussian noise in the remaining dimensions. Their theorem states small neural nets put more weight on the simpler feature. There are many assumptions, which we'll dissect later. Their math shows that the learned weights are the following. Let's parse this. There are three types of coordinates: linear, slab, and noise. The blue pieces are the same. The pink is what's different. The pink is positive, so the weight on the linear coordinate is larger. As dimension size increases, the weight on the linear coordinate also increases. This is what leads to the suboptimal situation we saw before.
Now we'll go into the dissection of the paper. The first thing we notice is that the paper lacks experiments using LSN and real-world data sets. The author's goal was to bridge the gap between theory and practice, but their results might not hold for real-world data that are highly correlated because they assume their data set is generally independent. Also, their most important theorem was proven on the LSN data set, but they failed to run any experiments on it. But we did, and we'll show you some limitations we found. The paper poses extreme simplicity bias as a widely found phenomenon, even in small dimensions. However, we found that it is not universal, especially in small number of noise dimensions. In the plot of our data, extreme simplicity bias appears as dimension size increase and the reliance on complex features decrease. It is worth noting that there are ways to mitigate the problem, including using a bigger model. We can talk about that later as well. The authors assume Gaussian noise and rely on its properties in their proof. This is questionable since real-life data is not necessarily Gaussian. We ran experiments using different types of noise, and our data shows that the threshold at which extreme simplicity bias appears in the dotted lines is pushed to higher dimensions. This may be because in a noisy distribution, gradient descent can fail to find the optimal path. Going forward, we could measure the effect of real-world noise on simplicity bias and explore noise removal techniques. Oh, there we go. 4, the authors based their paper on relatively small neural networks, namely a single hidden layer network. And they show extreme simplicity bias occurs in this case. However, our experiment with a more complex network manages to find a perfect classifier. And this may be because complex features can become simpler and higher dimensions. And so we would need to explain extreme simplicity bias for larger networks. Lastly, the theorem shows results only for weights after a single epoch of training. Certain features can take precedence later on in the training, and a similar result should be shown for later stages as well. This is a summary of our points, and thank you.
Awesome. Thank you so much.